let me mention one important thing. Electrical engineering course or program in general, and in particular a course or a lecture series on control systems, requires a fairly good bit of mathematical knowledge. And so one should not shy away from the mathematics or get unnecessarily scared by it. Like any subject, if you devote enough attention, you can learn the necessary mathematics, and it should not be thought of as an unfortunate burden that I would like to study the course, but what to do, there is a lot of mathematics in it, and is it really necessary, and things like that. Well, it is absolutely necessary. One is not using mathematics just because one has studied it or one wants to show off or anything like that. The mathematics is there simply because the systems cannot be described or studied without the appropriate mathematical concepts and ideas. Perhaps you can go to the laboratory and start a DC shunt motor without using any mathematical knowledge in that process. And of course, mechanics and workshop people all over the world, they have been doing this kind of a thing. They have been operating equipment without perhaps having the necessary mathematical knowledge to understand how the equipment works, why some things were not working satisfactorily, therefore changes were made, new designs were introduced, and so on and so forth. For the control engineer, a differential equation is something with which he or she has to be very familiar and not afraid of. That is, if I see a differential equation, I should not turn away from it or feel that it's an unnecessary bother, because as I told you earlier, that unless you are looking at things only in the steady state where everything is constant, and therefore only algebra and a little bit of arithmetic are all that are involved, when you are looking at changes, and the whole business of control and in particular feedback control is to cope with these changes, some unpredictable changes, variations, and so on. So when you are not looking only at the steady state, but you are going to look at the transient performance, things are going to be changing with time, and therefore effects like inertia, either mechanical, the moment of inertia, or electrical inductance, cannot be ignored, have to be considered, and the only way of considering them is through the use of the derivative. Of course, associated with an inductor, let's say, is flux linkages or what have you, and production of EMF. When the current in the inductor changes, a certain voltage appears across the inductor, and so on. But this is only qualitative. We need to relate the voltage associated with the inductor or the voltage across the inductor with the current associated with the inductor or the current in the inductor. And the only way in which we can relate it is through the derivative, by saying, okay, the voltage of the inductor is L times the rate of change of current, and there comes the derivative, and there is no way of avoiding it. Similarly, when a rotating body is being accelerated, there is angular acceleration, there is a torque required for that, and if you think in terms of speed, then the relationship between torque and speed involves derivative, because acceleration is derivative of the torque. So let us not be afraid of the mathematics, and let us learn it as and when it is required. Some of it you already have. In fact, you may have studied it in mathematics courses without knowing why you are studying it. For example, you may have looked at differential equations just like that, first order, second order, or whatever, and been asked to solve 50 differential equations of the same kind without being told, well, where do these differential equations occur? Of course, some examples from mechanics may have been given, but that they occur in electrical engineering or chemical engineering or aerospace engineering, etc., those examples may not have been presented to you. So it's time now to look at that. So we are looking at the solution of a ordinary linear differential equation with constant coefficient which was homogeneous, meaning that there was no input, or strictly speaking the input was 0, or the forcing function or stimulus was the 0 function. Then how does the system behave? So we looked at the first order differential equation, and we found out that it could be solved easily because fortunately we were familiar with the exponential function. By the way, this also means that you have to go beyond the simpler functions which one may have studied in school or even in the 11th and 12th standard. You do have to look into these more complicated functions, not too complicated, but the exponential, the sinusoidal function, the polynomial functions, and combinations of them, as we will see. These functions are unavoidable. In fact, you had studied a more complicated function, namely the logarithm, in school. So the first order differential equation solution just consists of an exponential with an appropriate coefficient of the exponent or an appropriate exponent. And in order to determine the solution uniquely, you need to have an initial or a boundary condition. Then we went on to study a second order differential equation, and one method that I talked about was to assume that the solution might be an exponential function, and then you discover that the exponent must satisfy a particular equation called the indicial equation. Fortunately, that equation is of the second degree or a quadratic, and one knows therefore how to find such an exponent or index m. It turns out that in general you will get two numbers, m1 and m2, as we saw earlier, and we looked at 3 or 4 different cases. And therefore the solution consists of a sum of two terms, sum of two exponentials with different exponents and with coefficients that multiply them, which will be different in general. And to determine the solution, you need to know two initial conditions. So for example, if xt is the solution, then it has k1 and k2 as the two parameters, or two unknown or undetermined coefficients, as they are sometimes called. Then we need two equations. Hopefully they will be enough to find out k1 and k2. And what are they? x0 is known or given, so that gives you one equation, and the derivative of x at 0 is also given, so that gives you the other equation. Hopefully these two equations can be solved to get a unique pair of numbers k1, k2, and if that is done, then we have got the solution, and we can confidently say that the system which was described by the second order differential equation with these coefficients a0 and a1 and with these initial values x0 and dx0 will behave like this, where m1, m2 are these numbers, k1, k2 are these numbers. We can then plot it either by hand or you can get a computer plot and things like that. So the differential equation can be solved. Now this is for second order or second degree differential equation. What do you do with a third order or third degree differential equation? It should be clear that this approach can be tried once again. The differential equation may be of third order, but I can try a solution which is again e raised to mt or k multiplied by e raised to mt, and then I will find that this m has to satisfy a third degree polynomial equation. It will be perhaps something like m cube plus a2 m square plus a1 m plus a0 equals 0. Find an m such that this is true. a2, a1 and a0 are the three coefficients that appear in the differential equation. So what must the differential equation be? The differential equation would be in our notation d cube plus a2 d square plus a1 d plus a0. This operator, polynomial differential operator, acting on x produces the 0 function. There is no input or 0 input. So x satisfies this condition. If x is assumed to be an exponential function with exponent m with a multiplying coefficient k, then m must satisfy this polynomial equation of third degree. Now unfortunately you may not remember the formula for the solution or for the roots of the cubic equation, although there is a formula, but that formula is fairly involved. Not only that, today one will not bother to use a formula, but one would rather use a computer program based on some numerical analysis technique to find out the solutions of such an equation, or to find out the roots or the zeros of a polynomial. And there is a good reason for that, and that's as follows. If I have a fourth order differential equation, I'll get a polynomial of degree 4, m to the power 4 plus a3 m cube plus etc. acting on x equal to 0. Note the way I am labeling the coefficients of the powers. A2 goes with m raised to 2, a1 goes with m, which of course is m raised to 1, and a0 I can think of going with a0 into m raised to 0. Therefore, in the fourth degree polynomial, the coefficient of m cube, I am labeling it as a3. That is, when I want to talk about the general equation, I will use this notation. For fourth degree polynomial also, there are formulas for the roots. The formulas are even more complicated than the formulas for the formula for the cubic, but there are formulas. Unfortunately, for degree greater than 4, that is 5, 6, 7 or whatever, there is no general formula. Unlike the quadratic case, where you had, if you remember, for the equation in the usual form ax squared plus bx plus c in school algebra, the roots were given by x equal to minus b plus minus square root of b square minus 4ac divided by 2a. So you had a formula which involved only the coefficients ABC. All you have to do is put those numbers in place of ABC, and you work out the required things: square, subtract, square root, whatever, and you get not one but two solutions. So there is a similar formula for a cubic and for the fourth degree polynomials. By similar, I don't mean necessarily involving only square roots, but there is a formula which involves these operations: addition, multiplication, subtraction, division, square root, cube root, fourth root, and so on. But for degree higher than 4, there is no formula, and not only there is no formula, there is no hope of anybody being smart enough to find a general formula. This is an important result in mathematics which we perhaps do not know at school level. It's not easy to prove it, of course, because one is saying that no matter how clever anybody may be, there is no formula for the roots of a polynomial of degree greater than 4 involving the coefficients of the polynomial and only these operations of addition, subtraction, multiplication, division, and extraction of a root: square root, cube root, fourth root, fifth root, whatever. If these are the only things that you are allowed to do, and these are the only computations that one can perform at school level also, certainly with a calculator one can do them, then there is no such formula, and therefore you have to use some approximation technique to find the roots of a polynomial of degree greater than 4. And these techniques can be used for polynomials of degree 4 and 3 also, although for a quadratic the formula is fairly simple and we have learnt it at an early age, and therefore we are not any longer afraid of using this formula rather than write a computer program or use a computer program that finds the roots of a quadratic. So in general, then one will have to use a computer program which is based on some numerical analysis technique of finding the roots, or because these are numbers which make the polynomial zeros, they are called the zeros of a polynomial. Now this turns out to be a very basic problem in a lot of control system theory. In particular, the control systems, the theory of what are called linear time invariant control systems, such as the motor problem that we are looking at. You come across this problem of finding the roots or zeros of a polynomial. If we use this e raised to mt approach, then of course we come across it right away, but we will see that when we use the Laplace transformation method, we will again come across the same problem of finding the roots of a polynomial. So this is a problem which you have to live with, and you have to find out, or you have to know rather, numerical methods of finding the roots of a polynomial. Fortunately, there are ready-made programs available. All you have to input to these programs is the coefficients of the polynomial. Of course, you have to do it in the proper order, and then use a command key or use a command, and you will get the numbers printed out, which are the roots of the polynomial. So it's as easy as that. But this is something which is involved in the solution of these problems. And of course, as I said, in the quadratic case, there were 4 different cases, and that is because the roots may not be purely real. They could be purely imaginary, or they could be complex. Also, the quadratic may have only one root, therefore we say it is one root repeated twice, or of multiplicity 2, or 2 coincident roots, but all I get is only one number from the formula. Similarly, the cubic could have only one root. It's quite easy to cook up examples. For example, I simply write m plus 1 cube, expand it out as a polynomial, and again from school days everybody remembers what this is. So m cube plus 3m square plus 3m plus 1, and now if I am looking at the polynomial equation, this thing is equal to 0. Well, there is only one number that will do the job. It's clear because it's m plus 1 cube. So the only root of this is m equal to minus 1. Now I may pretend that it is minus 1 repeated 3 times, and there is a reason for thinking of it that way, but what I get is only one number. Now if this is associated with the third order differential equation, then from this I will get only e raised to minus t, or k e raised to minus t as a possible solution. But that may not be enough, because you will actually find that this may not fit the behavior. Mathematically, that is because we can find out another function which also satisfies the same differential equation, but it is not k e to the minus t, but it is k t e raised to minus t. In fact, we saw this earlier for the second degree problem. For the third degree problem, then I will have to go one step further, and I will also have to think of k t square into e raised to minus t. And so what is called sometimes the complete solution, that is a formula which will include all solutions, will be given by k1 e raised to minus t plus k2 into t into e raised to minus t plus k3 into t square into e raised to minus t, or pulling out that e raised to minus t outside, e raised to minus t multiplied by, and I will change the notation for the reason that you know now. Instead of k1 I will call it k0, because it goes with the 0th power of t, plus k1t plus k2 t square. So this will be the general solution. That means the set of these functions for various values of k0, k1, k2, all of them will satisfy one and the same third order differential equation, which is d cube plus 3d square plus 3d plus 1 acting on x equal to 0, or even more compactly I can write d plus 1 cube acting on x equal to 0. One can show, of course, that the solutions of this equation are all included in this set. All of these are solutions, so this is the complete set of solutions. So this is called, usually in maths courses, the general solution. But that gives me infinitely many solutions, whereas I want to know what is going to happen to this particular system. Now for that, once again we need initial conditions, and this time there are 3 unknown or undetermined coefficients. So I may have to look for 3 initial conditions, and indeed one can show that given the 3 initial conditions x 0, that is the value of x, the response at 0, the value of dx at 0, and the value of d square x at 0, given these 3 initial conditions, one can uniquely determine these 3 numbers k0, k1, k2, what were unknown or undetermined coefficients, can be determined or will become known uniquely, and therefore it will give you a unique solution of the differential equation, but subject to the specified initial values or boundary values. Now this of course will apply to higher order differential equations of the kind that we are thinking of. So in general, for the nth order linear differential equation with constant coefficients and which is homogeneous, I will require n. If n is the order, I will require n initial values, x0, dx0, d square x0 and derivatives up to order n minus 1. And there will be these exponential functions e raised to mt with different values of m, and if there are not enough number of them because of this phenomenon of repeated roots, then they will be multiplied by expressions of this kind, t, t square and so on. So this is a result that we have, but 0 input is a very special case. In fact, it is hardly interesting. To operate a control system, you are going to apply some input. It is only as a special case that you may want to look at the 0 input situation. So what when the input is not 0? How do you get a solution or the solution of the system equation? And therefore you will say that, well, this is what will happen in the laboratory. If I go and set up and apply this input, this is the response that I expect to see. How does one solve therefore LDEWCC, which is not homogeneous, or which is said to be non-homogeneous, meaning that there is an input which is not 0, there is a forcing function, there is a stimulus. Knowing the stimulus function, knowing the forcing function or the input that is going to be applied, can I find out the solution of the system or the differential equation? How? That is the question. Now once again, before we go to the Laplace transformation method, which is the preferred method in control theory and which is the one which we will be using extensively, it is good to know that there are more elementary methods, elementary from this point of view, that you do not have to know what Laplace transformation is, which also perhaps you have studied in your mathematics, introductory mathematics courses. Let us take the first order differential equation. So I will write it as d plus a0 x. X is the response, x as a function of time, and bowing to control theory practice, on the right hand side I will not write y or f, which is very commonly done in mathematics courses, but I will write u. This is the preferred symbol for the input function u. So my problem will be find out the solution x if I am given u. For example, I may be told that ut, because this u is an input which may not be constant, ut equals sin t, and of course we expect that in order to get a unique solution I will require to know x0 also. So x0 will be some specified number, the input is specified as some particular function like sin t. Solve the differential equation, d plus a0 operating on x equal to u, or dx plus a0x equal to u. Now the technique that is used here, which can be then generalized for higher order equations of the same sort, is called the method of variation of constants, and this looks like something self contradictory. You are saying something is constant and then you are varying it, or a better expression is variation of parameters, and I will explain what is involved here. Let us look at the solution of the corresponding homogeneous equation, as it is called. That is, let us look at the case when u is 0. The equation is d plus a0 x equal to 0, and we already know the solution of it. The solution of it looks like k e raised to minus a0 t. So the equation d plus a0 x equal to 0 is said to be the homogeneous equation corresponding to the non-homogeneous equation d plus a0 x equal to u. That is, you simply put u equal to 0, what you get is the corresponding homogeneous equation. That equation we have solved knowing the exponential function, and the solution appears like k e raised to minus a0 t. Let us call this solution, let us give it a name, let us call it x0. So this is some known function. Of course k will depend on the value of x at 0. In fact, I can go further and write this as x0 into e raised to minus a0 t. X at 0 e raised to minus a0 t. Let us call this function x0. So I know the solution of the corresponding homogeneous equation for the given initial value. This solution is x0. For the first order case, extremely easy. For the second, third, fourth, we have to find roots of the polynomial, and then knowing the earlier theory, we know the general solution of the homogeneous equation. It will involve maybe not just x0 but also dx0 d square x0, or therefore it will have constants like not only k but k0, k1, k2 and so on. So let us look at this solution k e to the minus a0 t. This is the solution of the homogeneous equation. Now somebody, if I remember correctly, probably it was Lagrange, thought that the following might be helpful in finding a solution of the non-homogeneous equation, and he noted the following fact, that in the solution x0 of t we have this coefficient k which is unknown, undetermined, and it is a constant, in the sense this is not where t occurs in the exponent. But now I have u t on the right hand side, so things are going to change with time. So this will not of course be the solution. In fact, it will be the solution only of the homogeneous equation. So he made the guess that perhaps xt will look like kt into e raised to minus a0 t. So instead of just a number k, maybe there is a function kt which multiplies the exponential function. Can this work as a solution of the non-homogeneous differential equation? And you see the reason now why it is called the method of variation of constants or variation of parameters. What was constant for the homogeneous equation is now going to be replaced by something which varies, or which is another function of time for the non-homogeneous equation. Of course, this k, as I told you, is also called a parameter, parameter being a general term, resistance, inductance values and so on, initial conditions, all of them are referred to as system parameters in a general sense. So that is why it is also called the method of variation of parameters. Now when will this xt given by kt e raised to minus a0 t, when will it be a solution of the differential equation d plus a0 acting on x equal to u? Obviously this kt cannot be taken to be anything you like. For example, I cannot take it as constant, then that will be a solution only of the homogeneous equation. But what could this kt be? I have no idea. Well, let us try it out. If we want this to be the solution of the differential equation, then I will substitute on the left hand side and then equate it to the right hand side. So I will try d plus a0 of x with x given by kt into e raised to minus a0 t, try to work out what it is. Spend the next minute or two just working this out. Essentially all I have to do is d plus a0x is simply dx plus a0x. X is of course we have assumed it as kt e raised to a0 t, so a0x is very easy to determine. For the first term I have to differentiate x. Now this is not a big order, you just have a product of two functions, and as I told you, you cannot do control theory without knowing some calculus. So you had better be able to work out the derivative of that product without making any mistakes. Find out that derivative. It's easy. What is the derivative of x? And I will not use that t all the time. I have a product of two functions, k and the exponential function. So the derivative of x consists of two terms. One is the derivative of k, so I will write it as dk, into the other function which is unchanged, e raised to minus a0 t, plus k into the derivative of the exponential function. But what is the derivative of the exponential function? It is minus a0 e raised to minus a0 t. So this is the expression for dx. To that I add a0x, but a0x is simply k e raised to minus a0 t. So I add the two. So I get d plus a0 acting on x equals what? The interesting thing is this term cancels out. I have minus a0k e raised to minus a0 t, and I have plus a0k e raised to minus a0 t. So this e raised to a0 minus a0 t term, the exponential function which occurs in the homogeneous solution, cancels out, and I get therefore d plus a0x equal to simply dk, the derivative of k is not known, into e raised to minus a0 t. So the e0 t, e raised to minus a0 t has not disappeared altogether, it remains there, but I get it this, and this equals ut. If this x kt into exponential is going to satisfy the differential equation, then this must be equal to ut. Now this gives you a condition on dk, and it is very easy to find out the k which satisfies that differential equation. Once again, you should try to think about it for a minute. The problem is, I am given the function ut, for example ut may be sin t. I want to find the function k of t such that the derivative of k into e raised to minus a0t will turn out to be equal to my given function ut. Find out such a function k. Of course, it will turn out that such a function k will not be unique. There will be many solutions, in fact infinitely many, as we will see, but find out at least one solution. So spend a minute or two on this before looking at my answer. Fortunately, this equation is easy to solve for the reason that the factor e raised to minus a0t on the left hand side, which multiplies dk, is not 0. And I told you that this was an important property of the exponential function graph, that the exponential function graph never becomes equal to 0, no matter what anybody may tell you. The exponential function, which is a conceptual mathematical function, behaves like this. You have no choice. Practically, the exponential function may be dead, may be 0 after 5 time constants or after 10 time constants, and I had talked about time constants earlier, because practically 10 raised to minus 5 may be as good as 0, or maybe 10 raised to minus 10 certainly is as good as 0. That is practically speaking. But theoretically, conceptually, no, the exponential function is never 0. And therefore, I can talk about its reciprocal, and in fact, we all know that we have done these manipulations. The reciprocal of e raised to minus a0t is simply e raised to a0t. That is, 1 divided by e raised to minus a0t is e raised to a0t. Now, this much knowledge of the exponential function is obviously a must to proceed further. And as I told you, exponential sinusoidal functions, if you want to do control theory, better learn them very well. So I can solve that equation for dk as dk, the derivative of k, equals a product of two functions, not e raised to minus a0t now, but e raised to minus a0t multiplied by ut. So in particular, ut is given to be sin t, then I have e raised to minus a0t into sin t. And so I have to find out a function k such that its derivative equals this function. And I have made a mistake, if you have been noticing. What was my kt? Where did my kt turn out to be? Or e raised to kt was multiplied by what? Kt was multiplied by e raised to a0t. So in fact, I made a mistake which should have been corrected. 1 by e raised to minus a0t equals e raised to a0t. So when I get rid of the e raised to minus a0t on the left hand side, I do not get e raised to minus a0t on the left hand side. I get plus e raised to plus a0t on the right hand side. So make this correction. Now this, as you may realize, is really a differential equation of the first order, but not homogeneous, because the right hand side is not 0, it is non-homogeneous, but the left hand side is very special. Unlike d plus a0 x equal to u or 0, where we had d and a0, this one has only d k equal to some known function. So this coefficient a0 is 0, and because of this, to solve it, I do not really need to know or use the exponential function, but what I need to know is the operation of integration. Now just as differentiation, derivative, use of it, knowledge about it is a must, similarly integral, integration, knowledge of how to integrate, what is an integral, what are the properties of integration, all that is very essential in control theory. And we will see, you will see right now, right away why, because I have dk equal to something, I know the derivative of a function, I want to find the function. So what is the solution of this? And again, you should know that the solution is not unique, because there is always that there is something indefinite about the integral. There is always that constant which you have to put in addition to something else, in addition to the integral. And so this k is not determined uniquely. What is the solution of this? Dk equal to some function which is known. K is the integral of that function plus a constant term, and therefore I will write the solution as kt, the value of this function which we are looking for at time t, equals some constant. Let me call it, say, b0, because in some other cases there may be more than one constant or more than one coefficient. b0 plus integral, and I am writing what is called the indefinite integral, what is appearing on the right hand side. Now this is where we have to be very careful with the notation and with what we are doing. On the left hand side I have the value of the function at any particular time t that I may want to know. On the right hand side, therefore, what should appear? First of all, this indefinite integral is not adequate, so we have to make it a definite integral. Usually we choose the upper limit of the definite integral as t, the time at which you want the response to calculate the response. The lower limit can be any convenient time instant, and since I told you that most control system activity starts at some moment of time and then you operate the system, that is the so called initial time, and we have chosen to call it or represent it by the number 0, so we can choose the lower limit as 0. So we have a definite integral from 0 to t of a function. Now unfortunately the integral notation is such that we write there things like d of something, and therefore I should not write for our particular problem e raised to minus a0 t sin t dt, because this t that occurs in dt and therefore also occurs in sin t and e raised to minus a0 t is what is called the dummy variable of integration. Unfortunately the integral notation is such that we are used to it, or we have to get used to it. I would have preferred a different and much better notation for the integral, but this is more or less the standard notation. However, we have to make one change, and this change is essential for control theory, because otherwise without that you can get very wrong answers. And that change will be this dummy variable t which occurs under the integral sign, I will replace it by some other variable symbol or some other symbol. And it is common practice to replace the t, instead of t, have the Greek letter tau or tau. So I will write the expression or the solution as kt equals b0 plus integral 0 to t. The upper limit is t, which appears on the left hand side. The lower limit I am choosing as 0. I could choose it as 3 or 50 or minus 100 or whatever. And what is the integrand function? What is being integrated? E raised to minus a0, not t but tau sin tau d tau. Now here is a very small exercise for you to do after the end of the lecture. Calculate this integral, this definite integral. Integrand function is e raised to minus a0 tau sin tau d tau. The limits of the integration are 0 and t. Find out this integral. If you have done your calculus course successfully, you should be able to work out this problem. The result will be an expression that involves only t and not tau. That is why tau is called the dummy variable of integration. The expression will be something that involves only t and not tau. This is just an exercise in finding the definite integral of a function. The only thing is, the lower limit of the definite integral is a specific number 0. The upper limit is t, where t is any moment of time for which we want to know what kt is. So this t appears on the left hand side, it appears in the upper limit of the integral on the right hand side. Now that is kt, but my solution was not kt, it was kt e raised to minus a0 t. So I must put that. Secondly, what about this b0? How do I determine this b0? Well, put t equal to 0, then I have k0 equals b0. What about the integral? The integral is simply 0. That is a special case of an integral whose upper and lower limits coincide, and so the integral is 0. and therefore I simply get B0. So this B0 is nothing but K0. Now if I can find out what K0 is, then I know this B0. So I know this arbitrary constant, which is no longer arbitrary but is determined as K0. So if I can find out K0 somehow, I will get this B0. And so I will have found out the solution of the, or I will be led to the solution of the differential equation as Kt e raised to minus A0t. So let us do this. So now my xt equal to Kt e raised to minus A0t will be a solution of the non-homogeneous equation d plus A0x equals u. I have chosen ut equal to sin t, therefore in this particular case I get Kt, which is B0 plus integral 0 to t e raised to minus A0 tau sin tau d tau. This whole thing is multiplied by e raised to minus A0 t. This is the expression for x of t. Now this B0, which also happens to be K0, is the unknown constant. How to determine it? Let us put t equal to 0. So on the left hand side I have x0, and on the right hand side what do I get? The expression inside the rectangular brackets is B0 plus 0, so only B0. E raised to minus A0t at t equal to 0 is 1, so I will get simply B0. So this unknown constant, or the arbitrary constant B0, is not arbitrary now, it has to be equal to x0, the initial value of the response variable x. So if I substitute that here, then I can write the solution as follows: x of t equals B0 into e raised to minus A0t, but B0 we have determined to be x0, so I will have xt equal to x0 e raised to minus A0t plus, I will write that multiplier e raised to minus A0t up front, multiplying integral 0 to t e raised to minus A0 tau sin tau d tau. This is the solution because now there is nothing unknown. X0 is known, A0 is of course given, the integral can be evaluated, I have asked you to evaluate it. So this is the solution. Now we can see that the solution has two parts, that is, it consists of the sum of two terms. There is this term x0 e raised to minus A0t, which we had already encountered. In fact, it was the solution of the corresponding homogeneous equation d plus A0x equal to 0. The solution of this was precisely x0 e raised to minus A0t. So one part of the solution consists of just the 0 input or homogeneous equation solution. That corresponds to the case when the input is 0, and therefore it is quite natural to call it the 0 input solution. This is the response that you will get when the input is 0. Even though the input is 0, there is some response because x0 may not be 0. If x0 is 0, of course there is nothing, or the response is 0. So we will get the 0 input solution, which involves or which depends on the initial conditions, in this case x0, and it involves again the exponential function which goes with that exponent m which appears in the indicial equation and so on. So this is the 0 input solution, and naturally we expected this in a way, because when the input is 0 we should get something, and this is what we get. What about the other term? The other term depends on the input that we have chosen. In this case we have chosen ut equal to sin t or u tau equal to sin tau. So it is going to depend on the input, but it is what remains when the initial condition is put equal to 0. When x0 is put equal to 0, this part disappears and I only get this part. So what remains can legitimately be called the 0 initial condition solution, or I told you long time ago that one talks about the concept of state of a system, and so it is called the 0 state solution, and this 0 state solution depends on the input. And so the solution of the system or the response can be thought of as consisting of two parts, a sum of two parts, one the 0 input part and the other the 0 state part. Of course, when I go to the laboratory and make measurements, I am not going to get these two separate terms. these I have arisen while we were solving the differential equation. What I will get only will be their sum, x of t. So one has to look at what these two terms look like and then what their sum will look like, and that is what you expect to see. If I connect an oscilloscope for seeing some particular voltage or current variable, then the kind of waveform that I will get will be determined by the sum of these two terms and not by them separately. I do not experimentally get this separately unless I put input equal to 0. I do not get the 0 state response separately unless I put the initial condition equal to 0. But in the actual practical case, I will have a non-zero initial condition and perhaps and a non-zero input. When I have both of them present, I do not get these two things separately, I only get their sum. But it is our good fortune that xt consists of two parts which have this feature. One part, the 0 input solution, depends on the initial conditions only, or it is the solution when the input is 0. So, for some other input, of course, this part will be there, but there will be something more. The 0 initial condition or 0 state solution depends only on the input, and it will be there as long as the input is not 0. So, we have a sum of two terms. Now, the second term, the 0 state solution, can be written in the following way, and I am not going to go into any great details right now. Later on, when we may require it, I will use it and even spend a little more time on it. But what can be done is, we have this e raised to minus a0 t outside, the integral sign 0 to t, the upper limit is t. Inside we have minus a0 tau multiplying the input function sin tau d tau. Tau is only the dummy variable, this d only tells you that you are integrating. In place of sin tau, in general, I can think of my input u tau. In fact, unless I am actually calculating, it makes no difference whether I put u tau there or sin tau. So, I might as well put u tau. So, for an arbitrary input u tau, this will be the part. Now, what one can do is, this e raised to minus a0 t, which appears outside the integral, can be pushed inside the integral, and this is where some trickery is required and care. What is inside or under the integral sign has only tau, and therefore we are justified in pushing this e raised to minus a0 t inside the integral. Now, this requires some careful argument. I am not going to give it or go into it, but if I do that, then what will I get? Integral 0 to t, then I will have e raised to minus a0 t in the equations that you may have copied. So, I have this e raised to minus a0 t, okay, but under the integral sign I have plus e raised to a0 tau multiplied by sin tau d tau. That is what I have. Now, I will rewrite it further, and right now you may not see much reason for doing it. I will rewrite it as integral 0 to t e raised to minus a0 into brackets t minus tau, that is, this a0 multiplies an expression in parenthesis which looks like t minus tau. Just check, e raised to minus a0 t, e raised to minus a0 minus tau, that is e raised to a0 tau. So, that is okay. Nobody can prevent me from writing it like this. This multiplied by u tau d tau. Now, such an integral is called a convolution integral, and the reason for writing this e raised to minus a0 t minus tau is the following. My 0 input solution that I had talked about, I had called it x0, was simply xt equal to x0 into e raised to minus a0 t. So, if I look at the special case when x0 equals 1, then the solution is simply e raised to minus a0 t. So, this minus a0 t is the solution of the homogeneous equation when the initial condition is 1, x0 is 1. Now, so this is one special solution of the homogeneous equation. Homogeneous equation, therefore, right hand side is 0, but initial condition equal to 1. So, if I denote this by x0, and this is what I did earlier, because that k was being replaced by kt, then the above integral, this one, can be rewritten as integral 0 to t. This exponential term can be written as x of x0 of t minus tau u tau d tau. So, I have the function u, which is the input function. I have the function x0, which is a particular solution of the homogeneous equation for a particular initial condition. Then the integral looks like this. It is not product of the two functions, it is not x0 tau u tau, but it is x0 t minus tau into u tau integrated from 0 to t, and this is said to be the convolution of x0 with u. This operation is referred to as doing or taking the convolution of x0 and u, the convolution of two functions, the input function and a particular response of the system. Now, this particular response, for some historical reasons, gets associated with something which is called an impulse function, and we will look at this when we use the Laplace transform approach, and therefore, this x0 has been called the impulse response of the system. One has to be very careful in understanding these expressions, because as we will see, the impulse function, strictly speaking, is no function at all. That is, it is something with which you cannot really do mathematics, and therefore, to talk about response to the impulse function will be going one step beyond what you are allowed to do. And in practice also, we do not have anything like the impulse function input, practically speaking. However, let us keep aside that thing for the moment. Simply remember the term impulse response. And so, the 0 initial condition response, or the part of the response that depends on the input, appears as a convolution of the impulse response with the input. This operation of convolution has some interesting properties. It is something which can be actually, of course, worked out, and I asked you to solve that integral or find that integral. So, without telling you that you were doing the operation of convolution, you would have done it. It can also be given a graphical interpretation of what is happening. Integral of a function has the interpretation of area under a curve. Now, if you have the integral of a product, and the product is this in this peculiar way, so what does it mean graphically? It can be given a meaning, and that is the reason why the term convolution is used. In fact, this was done, this idea and this interpretation was done first by German mathematicians, and they used a term which is called Faltung, which means a folding. That is, in their interpretation, or in the interpretation that of course you and I can use and you will use, something like folding, an operation of folding is involved. Not only folding, but then folding, shifting, multiplying, and then finding the area under the curve. So, they use the word Faltung. The integral was known as a Faltung integral, and when this term was translated into English, somebody invented the term convolution. Although convolution is not really exactly folding, it is really something which is twisted around in some various ways. That is said to be something which is convoluted. A convoluted surface is a surface which has all kinds of twists and turns and folds and depressions and projections and what not. That is said to be a convoluted surface. So, the name convolution integral and convolution of two functions arose out of that. And so, this is what we have then. The solution of the system with a non-zero initial condition and with a non-zero input will be a sum of two terms, one of which will be the solution of the homogeneous equation with the initial conditions, and the other will be the solution of the equation with 0 initial conditions and input, and that can also be thought of as the convolution of what is called the impulse response of the system and the input, and the impulse response can be thought of as response of the system to a certain function called the impulse function under certain very appropriate initial conditions. Now, this of course we did only for the first order differential equation. The same approach extends to the second order differential equation and higher order differential equation. Of course, in the case of the second order differential equation, there are two values of m in general, and there are two constants or coefficients or parameters k1 and k2, and so you will have to think of varying both of them and then get some expressions for those multiplier functions k1 of t and k2 of t, and thereby get the solution. One can put it in exactly the same form that we have got for the first order case. A 0 input part which depends on the initial conditions and a 0 state part which is a convolution. So, whether the differential equation is of first degree or second degree or fifth degree and therefore nth degree, so to speak, the solution is fortunately given by the same form, a 0 input form, which of course will involve exponentials and coefficients which are to be determined based on initial conditions, and a 0 state part which requires knowledge of the input and which can be carried out through the operation of convolution or evaluating an integral, which involves a product of the input function with something which goes or which appears in the 0 state response, in the 0 input response, or specifically it is the impulse response of the system. So, this is one way of solving the system differential equation for an ordinary linear differential equation with constant coefficient which may be non-homogeneous. We can find the solution if we know appropriate number of initial values and if we can evaluate certain integrals involving the input function and the impulse response of the system. Finding out the 0 input response or the impulse response of the system requires finding the roots of a polynomial equation or the zeros of a polynomial, or to go back to school algebra, it requires factorization of a polynomial. So, that is one basic numerical problem that one has to solve. Once you solve that, you get these exponential functions. Then the other problem is of course carrying out the integration. Now, today of course all these can be programmed, so that there are program packages where you just specify the initial conditions, you specify the derivative coefficients, you specify the input function. It may be given explicitly as sin t, or you may give its values at instants of time, and the program will calculate and plot for you x of t. What has to be remembered is that no matter how impressive that plot is, what the program does is only finds an approximate solution and not the exact solution. It looks very nice, but that is only an approximation to the solution. How good the approximation is depends on what program you have used, how many discrete steps you have divided the time interval into, what is the accuracy of your computer or precision rather, single precision arithmetic, double precision arithmetic, and so on. What you get is only an approximate solution, but the approximation is reasonably good most of the time.